Okay, folks. So my plan for today is to continue the discussion of the PIO subsystem that we started last time. And in particular, I'd like to very briefly go through and review some of the concepts that we hit in the last lecture. Last lecture was a lot of information really quickly, so I want to just go back and reinforce that very briefly. And then there's a handful of more concepts that I want to introduce. And then what I'd really like to spend the bulk of this lecture doing is reinforcing these concepts using some concrete examples. And in particular, I want to start with some really simple PIO examples. We'll start, in fact, with just using a PIO program to generate a square wave output. And then we'll look at increasingly complicated examples, ultimately working our way up to the VGA driver that we're using for Lab 2 and that you also used in Lab 1, which is the PIO implementation of the VGA standard for communicating to the 640 by 480 VGA screen. And I'll just remind you that this is worth knowing because if you want to get the most Boids that you possibly can in Lab 2, you'll need to go in and modify this PIO program. Okay, so that's the plan. Let me start by just really briefly reminding you what we took a look at last time. So we started by looking once again at this schematic view of everything contained in the RP2040. And we were just looking at this to point out that what we are talking about are these two PIO coprocessors down here. And if we zoom in to one of these PIO blocks, as they're called, we'll see that it contains the following. Each PIO block can contain up to 4 state machines. You can think of these state machines as completely independent programs. There are mechanisms by which one state machine can signal to another state machine. So you could, for instance, have state machine execute a series of instructions and then wait until signaled by state machine 0 before executing some other sequence of instructions. So they can communicate via flags, or as the PIO assembler language calls them, interrupts. But you can think of these as 4 independent programs that can live on a single PIO block. And the fundamental limitation that we have to deal with is that the sum total number of instructions contained in all 4 of these programs may not exceed 32. So we have 32 instructions to spend per PIO block, and those instructions can be distributed among up to 4 separate state machines or 4 separate programs. These programs communicate to the outside world via a direct connection to the GPIO ports. So a PIO state machine can write to any of the GPIO ports, up to all of them, and it can read from the GPIO ports as well. And then the interface between the PIO subsystem and the ARM looks like a whole bunch of FIFOs. So there are 2 FIFOs connected to each state machine. One is for communicating data from the system, that is to say the 2 processors or the ARM, into the PIO program, and the other is for communicating data in the other direction, from the PIO program back to the processors. And the way that this often works is if we're implementing some sort of a communication protocol, maybe we're implementing an SPI connection or an I2C connection or a VGA connection, the way that this often works is we dump the data that we want communicated to the peripheral, the external peripheral device into one of these FIFOs. It gets sucked into a PIO state machine, and ultimately that data is put out onto the GPIO ports according to our PIO implementation of whatever communication protocol it is that we're communicating through. And then likewise, if the device that we're talking to can talk back to us, it may be the case that this state machine pulls data in off the GPIO ports, puts them into the other FIFO for communication back to the processors to do whatever you want to do with it, right? And the most powerful way to facilitate that communication is to point DMA channels at these FIFOs, and we'll look at examples of this. There are other methods of communication. You can have the C SDK allows for you to in your C code, like in the software that's actually running on the ARM, you can write data in software to these FIFOs and read data from these FIFOs in software. But for really, really high bandwidth communication, you want to hook up DMA channels. And then the other method of communication between these state machines and the processors is via interrupts. Each can throw interrupts that are visible to the processors. And you could tie an interrupt service routine to that processor so that some action is taken when a particular state machine throws a particular interrupt. And then if we zoom in one more level, so I'll just remind you, there are 2 of these PIO blocks. We've zoomed into one of these PIO blocks, and in that PIO block, there are up to 4 state machines. We can now zoom in a bit further into one of these state machines and look at what's contained in one of these things. And what we discover is that there's not that much in these things. Each state machine contains 4 registers, 4 32-bit wide registers. One of those registers is called scratch X, where it is what it sounds like. It's just a scratch register, so you can use it. A common use for it is to keep track of, use it for things like counting instructions. You could put a variable or a number in there that gets decremented so that you can count how many times a particular instruction is executed before moving on to a next instruction. So there's 2 such scratch registers, scratch X and scratch Y. There's also the output shift register. This is also 32 bits wide, and this is connected to the TX FIFO, one of these FIFOs that communicates with the rest of the system. And likewise, there's a input shift register that communicates the RX FIFO, the other FIFO. There's also a program counter, which is keeping track of which instruction is presently being executed. Generally, if you have a PIO program that is simply a list of instructions that doesn't include a jump, then what this program counter would be doing is just incrementing. So we start with instruction 0, then we go to instruction 1, 2, 3, 4, etc., until we get to the last instruction, at which point this would wrap back to 0, and we would start executing from the top of the program again. As we'll talk about in more detail today, and as we talked about last time, there are instructions in the instruction set for these PIO coprocessors that allow for you to conditionally move this program counter. You can execute a jump. So you can jump from one instruction to, a specific instruction further up in the program, or you can alternatively have a jump over a bunch of code to some instructions that are further down, right? So you can use these jumps to jump around the program. There's a clock divider so that you can slow down the execution of your PIO program relative to the system clock. We'll see this in the VGA example. And then there's some control logic. And the last thing that we talked about last time is we walked through each of the 9 instructions, that you can implement in a PIO program. So any PIO program will contain a list of instructions, and this is the full set of instructions that any such program might include. And we talked through them in detail last time, but generally speaking, they fall into one of 2 categories. Well, okay, maybe 3 categories. A subset of these instructions, all that one subset of these instructions does is move data from one place in this state machine to another place in this state machine. So where are the places where data might be moved to and from? Well, you might move data from the TX FIFO into the output shift register, or you might move data from the scratch Y register into the input shift register, or you might move it from, the output shift register to the GPIO pins, right? This is what I mean. The places from which data can be moved to and from in a particular PIO program include the 2 FIFOs, the 4 registers, and the pins. And a large subset of these instructions just move data from one of these places to another one of these places. With a few details to keep in mind, like some of them allow for you to move a certain number of bits from one of these locations to another one of these locations. But okay, we can come to those details in a bit. In particular, in fact, let me put these 2 diagrams on the same slide here. So let's take a look at this. So in particular, the in command, all that the in command is doing is moving data from some specified source into the input shift register. So you specify where you would like that data moved from, And so you might say, I want data moved from the X scratch register into the input shift register. I want data moved from the Y scratch register into the input shift register, or from the input shift register into the input shift register, which is essentially a no-op, right? From the output shift register into the input shift register, or from the pins into the input shift register. Those are your options. But that's all that in is doing, is saying, I would like data moved from a specified source into this particular register. And out is very similar. An out command is just saying, I would like data moved from the output shift register to a specified destination. And those destinations might include the X or Y scratch registers. It might include the input shift register. It might include the output shift register, which again would be like a no-op. It might include the program counter. So you could say, I am modifying the program counter with an out command. It might alternatively, and maybe we'll come to this. This is getting a little twisted. But you could say, I would like whatever data is contained in the output shift register to be executed as an instruction, right? So remember that. Let me just pull up the data sheet here. Remember that all of these PIO instructions are just 16-bit wide values. So if you have some 16-bit wide value in your output shift register that makes it look like one of these instructions, you could say, I would like whatever data is contained in that register to be executed as an instruction. You can imagine that things could get pretty complicated pretty quickly when you start doing that stuff. The programs that we look at won't take advantage of that, but some of you might definitely want to do such things for your final project. It'd be pretty interesting. So okay, in just moves data from some specified source into the input shift register. Out just moves data from the output shift register to some specified destination. Likewise, the push command here, all that that's doing is moving data from the input shift register out into this FIFO so that it can be gotten by a DMA channel, for instance. Likewise, pull is just moving data from the TX FIFO into the output shift register. So suppose you have some DMA channel that dumps some data into the TX FIFO, a pull will move that data into the output shift register. And then incidentally, you could have that DMA channel set up such that it will do a new transaction whenever this FIFO is emptied, so that as soon as your state machine pulls data out of the FIFO, the DMA channel puts more data in. We'll look at that. The VGA driver takes advantage of that. What else? So I'll just remind you, we are considering the subset of these instructions that just move data from one place to another place. So in, out, push, pull, move, perhaps obviously just moves data from some specified source to some specified destination. So those sources might include the X or Y scratch registers, might include either the input or output shift registers, or might include the pins. And the destinations might be any of those places again. Or you can also have, you can also use a move to execute the data that you're moving as an instruction as well. That command allows for that. That instruction allows for that as well. So all of those instructions that I just mentioned, all that they do are moving data from one of these places to another of these places. The set command is similar but a little different in that the set command is allowing for you to specify the data that you would like to place within either the X scratch register, the Y scratch register, or the pins, subject to the one limitation that you can see in this table here. The width of the data part of this instruction is only 5 bits. So you can set the value of the X or Y scratch registers with values up to 2 to the 5th. And likewise, you can set the values of up to 5 different GPIO ports using a set command. If you want to set more pins than that, or you want to set these values to something other than, to a value greater than 2 to the 5th, then you need to use another one of those commands. Perhaps, for instance, you put some large number into the TX FIFO, use a pull command to move it into the output shift register, and then a move command to move that value from the output shift register into the scratch X register. And that would be a mechanism by which you could get a larger number than the set command allows for you to specify into that scratch register. It involves a little bit of extra footwork, but it's not so bad. So let me just summarize that in, out, push, pull, and move, all that those are doing is moving data from one place to another place. Set is allowing for you to specify the data that you would like to have contained within either the X or Y scratch registers or the GPIO pins. And then all of the instructions that I didn't mention, they don't move data from one place to another place in one of these state machines. Instead, they allow for you to control the flow of the program. So the jump command, for instance, allows for you to move from a particular instruction to some instruction that isn't the next one. So you could say, I would like to jump back up higher in my program, or I would like to jump down lower in my program. And you can specify the conditions under which that jump occurs. We looked at that last time. Likewise, sort of, wait allows for you to have your program stop executing until some condition is met. So this is a good, you could, for instance, have your program sit and wait until a particular pin goes high or low. Why might that be useful? We'll see some examples of this, but suppose you are implementing a UART receive channel in PIO. You would want for your PIO program to sit and wait until it sees that start bit that we talked about last time, right? So the program would sit and wait, and as soon as the receive pin went low, it would start executing the logic associated with receiving a UART transmission. Or likewise, maybe you have your program sitting and waiting until a chip select line drops, right? So you can wait on the value of a pin. You can also wait on one of these interrupts that I mentioned briefly earlier. You could have state machine 0 throw an interrupt, and meanwhile, state machine 1 would be sitting on a wait instruction until it sees that interrupt has been thrown. And then that would be a method by which those two independent state machines could then be synchronized. And did I miss any here? I don't think so. So we talked about jump, we talked about wait, we briefly talked about jump and wait. We talked about in, out, push, pull, move, interrupt, and set. Okay, and I'll just remind you that what I have given you is sort of a hand-wavy, somewhat high-level summary of these things. The data sheet includes a long description of each of these instructions, including all of the options associated with a particular one of these instructions. Options being things like, you know, for a jump command, what are the conditions under which we want for that jump to take place? Do we want for the jump to take place when the scratch register is 0, or when the scratch register is non-zero prior to a decrement? So we are both checking the value of the register and then decrementing it in a single cycle. Same with Y. Do we want for the jump to take place conditional on the value of a pin, or conditional on the emptiness or not emptiness of the output shift register, right? So there are a bunch of options associated with jump, and likewise for the other commands, right? So, you know, what are the conditions under which we're waiting, and so on. So you can read about all of these. What I want to talk about before we start looking at some examples is there are a handful of other configurations that you can make to these PIO programs to save yourself some instructions. And because we only have 32 instructions to spend, it's nice to know about these things that can save you one or two. They end up being worth it. So I want to talk about a few of these. In particular, I want to talk about Autopush and Autopull, and I want to talk about something I forgot to include here, which is wrapping. So let's do this by looking at the data sheet. So we can scroll down here Oh, and I want to talk about side sets too. And beneath all of the descriptions of the various instructions, we will find a set of other functional details and possible configurations. One, the first thing that we find in this section of the data sheet is a description of the side set feature of these PIO programs. A side set allows for you to simultaneously with executing some instruction, one of those 9 instructions that we just talked about. So in a line of a PIO program, you can have the instruction with all of the details associated with that instruction. And then next to it, you can see the word side and then some value. And that is telling that is an instruction to the PIO coprocessor that simultaneously with executing the instruction, you would like to set or clear some set of GPIO pins. So this side set allows for you to manipulate the value of up to 5 GPIOs simultaneously with executing some set of instructions. So you could, for instance, say, move X, Y, side 1, which would be an instruction to move the data that's contained in the Y scratch register into the X scratch register. Oh, and also, by the way, please set the pin that I've configured as the side set pin to a value of 1. So this is allowing for you to execute a series of instructions and manipulate 5 GPIO ports at the same time. We'll see why this is useful. What this is really, really useful for is things like implementing SPI channels, where you want to do things like toggle the clock line and read the data on the data line in the same cycle, right? This allows for you to do that. You can set up you can use these side set features to manipulate the clock, which is going high, low, high, low, high, low. And meanwhile, at the same time, you can be reading data in from the pins using an in command into the input shift register, which you can also ultimately pop into a FIFO for communication back to the ARM. When we look at example of the SPI the PIO implementation of an SPI channel, we'll see this. Okay, so we'll see side setting. Program wrapping is another thing that I wanted to talk about. Program wrapping is a method by which you can save yourself jump commands. So suppose that you have some PIO program, and in that program, you want for some number of instructions to execute only once, and then you want for the rest of the instructions to be executed over and over and over and over again, right? So for instance, maybe you have a small number of instructions that are responsible for, say, pulling some data in from the FIFO to do things like initialize register values or something like that. And then forever after that, you want to just loop over some other set of instructions over and over and over and over again that's perhaps using that data to, I don't know, set a PWM output or something like that. One method by which you could do that is you have your series of instructions, and then, so you have your series of instructions that executes once, you have your series of instructions that you want to have executed over and over and over again. And at the bottom of that set of instructions that you want to have executed repeatedly, you would have a jump instruction that would point the program counter back to the beginning of the set of code that you want to have repeatedly scheduled. And then what would happen is you'd start the PIO program, the program counter would start at instruction 0, move to instruction 1, 2, 3, 4, 5, etc. Ultimately, it would get to the jump instruction. And if you had it jump back to instruction number 3, then the program would then just loop from instruction 3 to the end of the program over and over and over again, and it would never run that first set of instructions again. Okay, so that's one way that you could do it. And it costs, in order to do that, it costs you a jump command, a jump instruction, which is one of the 32 that you have to spend. Program wrapping allows for you to specify a wrap target. So you can see an example of this here. So this is implementing a square wave. So you can see that there is a single instruction, there's a set instruction here that we want to have implemented once. So this is a set, the the value that we are setting is pinders. If we write to pinders, we're specifying whether we would write for this, like for the set pins to be input or output. So in any case, we set the pin to an output. We only want for that to happen once. And then forever after that, we want to set the pin high, wait for a cycle. This bracket 1 is an instruction to pause on this command for 1 extra cycle. This delay occurs after the instruction. So what will happen here is we'll hit this instruction, the pin gets set high, we wait for an extra 1 cycle, and then we'll move to the next instruction, which sets the pin low. We then wait for 1 extra cycle. And because we have this wrap and wrap target directive here, without using a jump command, this PIO program will loop forever between these 2 wrap directives. So this is a method by which we can have initialization code and repeatedly executed code without spending a jump instruction, which, depending what you're doing, depending how many instructions you have to spare, might be nice to know about. FIFO joining I briefly mentioned. So suppose you are implementing a one-way interface. So suppose that you are only ever going to be, you're communicating with some external peripheral and you're only ever going to be talking to it. You're never going to have it talking back to you. In that case, it might be the case that you have no use for the FIFO that goes from the state machines back to the processors. If you have no need for those FIFOs, the system allows for you to combine the RX and TX FIFOs into a single FIFO. So independently, the RX and TX FIFOs are 32 bits wide, 4 samples deep. You can combine them into a single FIFO that is 32 bits wide and 8 samples deep that is one directional, either just from processor into PIO or just from PIO back into processor. Perhaps useful. Autopush and autopull. This is in the way that that program wrapping can save you a jump instruction. Autopush and autopull can save you push and pull instructions. And what this allows for you to do is whenever you implement an out instruction or an in instruction, one of the required arguments to that instruction is how many bits would you like to have shifted out of the output shift register or into the input shift register? Do you want to move, all 32 bits from the output shift register to somewhere else? Or do you only want to move 4 bits or 3 bits or 1 bit or whatever it is? You specify the number of bits that you would like shifted out. There is a shift counter that is counting the total number of bits that have been shifted out of the output shift register or into the input shift register. Autopush and autopull allows for you to configure a threshold for that shift counter such that whenever the system counts some threshold number of bits have been shifted out of the output shift register, it will automatically execute a pull instruction to go get data from the TX FIFO and put it back into the output shift register without you having to write pull, without you having to spend the pull instruction. And likewise for push, right? So suppose that you are shifting data into the input shift register. So suppose you're pulling data in off of a pin 1 bit at a time. And once you've executed that 8 times, so you've shifted 8 bits into the input shift register, you can configure auto push such that when it counts a certain number of bits have been shifted into the input shift register, it will automatically execute a push instruction to move the data from the input shift register back out to the RX FIFO for communication back to the processor. And that saves you a push instruction. So this is nice to know about. All these things are nice to know about because when you only have 32 instructions to spend, it's nice to know little tricks to save you a jump, save you a push, or save you a pull. So wrapping will save you jumps. Auto push and auto pull can save you pushes and pulls. And they're easy to set up. We'll take a look at them. Anything else to mention before we look at some examples? Clock dividers, I mentioned briefly. You can specify that, suppose that your system clock is running at, I don't know, 125 megahertz, and you would only like for your PIO state machine to execute at 25 megahertz. You can put a divide by 5 clock divider. You can configure your PIO state machine such that it will divide the system clock by some specified value. So if you made that specified value 5 for 125 megahertz system clock, then your PIO instructions will execute at 25 megahertz instead of 125 megahertz. That can be nice because if the interface that you are trying to implement is slow relative to the system clock, slowing down the PIO program can save you instructions, because I mentioned previously that that bracket, let me scroll back up here and find an example. This bracket next to the instruction is specifying the amount of cycles that we would like for this instruction to delay after having executed. And if we scroll back up and look at the set of instructions here, that table that we've been looking at quite a bit, sorry, just scrolling, this table here, you can see that we only have 1, 2, 3, 4, 5 bits that we can spend on a delay, which means that you can only ask for a particular instruction to delay for up to 32 cycles. So if you're implementing a slow protocol and you need for a particular part of that protocol to delay for a lot of system clock cycles, you would end up having to repeat that instruction a number of times in order to have that instruction last as long as you want for it to last. Alternatively, if you slow down the whole PIO program relative to the system clock, then you don't have to necessarily have repeated identical instructions in order for that instruction to last as long as you want for it to last. I'll just briefly mention too that you can see that these bits are labeled delay/side set. So I mentioned earlier that that side set feature allows for you to set the values of up to 5 GPIO pins simultaneously with executing some instruction. Those 5 bits that specify the GPIO pin values are shared with the delay. So suppose that you have 2 pins that you would like to manipulate with side set. That removes 2 bits of delay. So that means you now only have 3 bits to spend on delay. So instead of being able to specify delays of up to 32 cycles, you can instead only specify delays of up to what? 8 cycles, if I did that right. In any case, you are sacrificing delay for side set GPIOs. Everything's a trade-off. Okay, I think I want to pull up an example here now, but let me just make sure I'm not forgetting anything. We talked about that. We talked about that. GPIO mapping. We'll look at that in the examples. I think that's the clearest place to talk about it. But a whole set of these instructions allow for you to manipulate the GPIO pins. So you can manipulate GPIOs using a set. You can manipulate them using an out, and you specify which pins you're talking about when you say like set pins 1. You have to configure which pin that means. We'll see this in the example code. Anything else that I want to mention about here? I don't think so. So let's now look at some examples. And the place that I'm going to go to find these examples is we have been spending, let's see. So there is this repository that contains the demo code that I've put together for the course. In the first week of class, I mentioned that there was another repository of demos that you might find really useful. And that repository is the Pico examples repository that's put together by the Raspberry Pi company. It's super easy to install if you follow essentially exactly the same instructions for cloning and building the 4760 demo repository. You can clone and build this repository of demos from the Raspberry Pi company, which includes demonstrations of all the bells and whistles in the RP2040, the ADC, all the clocks, the DMA channels. What I want to look at in particular are their demos associated with the PIO subsystem. And I want to look first at this hello PIO example, which, as you can see, it contains, there are 3 files contained in this project. This is the simplest PIO demo in this whole repository. So I think it's the appropriate place to start. There's a .pio program, which contains our PIO assembly program, and there's a C program, and then the CMake list, of course. So let's just look at the PIO program here. And what we'll see is there's some things to get used to syntactically here. One of the things to get used to is a semicolon is used for comments. So everything to the right of a semicolon is a comment. The PIO program starts with a dot program and then the name of the program that we are implementing. So we're calling this program hello. Loop here is not an instruction. This is a program label. So when we execute a jump instruction, we can point it back to this particular label. And then all that this program is doing is executing a pull. So I'll just remind you that all that a pull is doing is moving data from the TX FIFO into the output shift register. It's then calling an out, which I'll just remind you moves data from the output shift register to a specified destination. In this case, the destination is the pins, and the other argument to the out command is the number of bits that we would like shifted out. And in this case, it's 1. So we are shifting 1 bit out of the output shift register to a GPIO pin. And then we're executing a unconditional jump instruction. So this jump instruction always executes, that moves us back up to the pull here. So what will happen is we get whatever data is contained in the TX FIFO and move it to the output shift register. We then shift a bit that's contained in the output shift register out to the pins. We then jump back up and do it again. By the way, what if there is no data in the TX FIFO? So there's no data for this to pull. What happens? Well, actually, you get to decide. So if we take a look at the pull instruction here, we have a few options associated with pull. So let me see. So in particular, there's this block option. So if we call pull block, what that means is execute a pull instruction. That is to say, move data from the TX FIFO into the output shift register. Pull block means if there is no data in the TX FIFO, then stall. Stall on that instruction until data appears in the TX FIFO. And incidentally, that is the default, right? So if we don't specify a pull block or no block, then it defaults to a pull block. So in the program that we were just looking at, if there's no data in the TX FIFO, the program stalls here on this instruction until data appears in the TX FIFO, at which point it moves it in one cycle. It moves it from the TX FIFO into the output shift register. Alternatively, we could specify pull no block, in which case it will move data from the TX FIFO into the output shift register if there is data to be moved. In the event that there is not data available to be moved, it will instead move whatever data is contained in the X scratch register into the output shift register, which suggests that you might want to put some default value in the X scratch register if you're going to do non-blocking pulls. And then the other thing that we can specify is the other option associated with pull is this if empty, which is sort of similar to that auto push and auto pull thing that I was talking about earlier, where I'll just briefly restate that what auto push and auto pull is doing is, well, let's talk about auto pull in particular. Auto pull is keeping track of how many bits have we shifted into the output shift register. How many bits have we shifted out of the output shift register? And when we count a certain threshold number of bits, it automatically pulls again without us having to spend that instruction. A pull if empty, when we get to a pull command, a pull instruction, and if the if empty option is asserted, then it will execute that pull instruction only if that shift counter has reached the specified threshold. Otherwise, it passes right through. Which is just to say that this line of code here, it will move data from the TX FIFO to the OSR if there is data in the TX FIFO to be moved. Otherwise, it sits here and waits for that data to appear in the TX FIFO. It then moves 1 bit from the OSR out to the pins and jumps back to the beginning. So if we were to, okay, so then let's look at the C code. Let's look at the C code. So now if we look at the C code, there's not that much going on here. So all that we are doing is we are instantiating a PIO object, and we're calling it PIO0, much like when we are configuring a particular SPI channel, and we said it's either going to be SPIO0 or SPIO1. We have to choose which PIO instance we're going to use. Remember that there are 2, so we're going to use PIO0 or PIO1. In this case, we're using PIO0. We then add that program, the hello program that we just wrote, to PIO0. We claim one of the state machines on PIO0. Remember that there are 4. So this instruction here, much like there's a similar instruction here that we've seen before for claiming an unused spin lock. So remember that there are 32 spin locks, and you can specify which one you want to use, or alternatively, you can call an SDK function that will hand you an unused one. Much like that, we could, if we wanted, specify the particular state machine on PIO0 that we wanted to use. We could specify it as 0, 1, 2, or 3. Or alternatively, in line 28 here, we're saying, please give me one that's not used. And then we initialize the program. So the arguments to this function include the PIO instance that we're using, PIO0 or PIO1. In this case, we're using PIO0 as specified up here in line 17. We specify the state machine on PIO0 that we're using. We specify the offset in that instruction memory where we're placing this particular program, and that's calculated here. We aren't specifying that. We aren't specifying that ourselves, so to speak. We're instead calling an SDK function that will give us an offset based on what else is on that PIO block and how long our program is. And then the last argument here is the pin that we are going to configure as that output pin that we're manipulating. Incidentally, where does this function come from? Well, the convention that the demo code uses, and one that I think is a good one, is in the .pio file here, in addition to the PIO program up above, there is an initialization C program instantiated down below that configures the PIO program up here. So this particular program is called hello program init, and as an argument, it takes which PIO instance we're using, PIO0 or PIO1. It takes which state machine are we using on that PIO instance. It takes the offset in instruction memory, which we had an SDK function provide to us. And then it takes as an argument a pin number, a GPIO number, that will get mapped to this output pin. And then this function does all of the configuration of this PIO program. Configuration meaning things like setting up if we cared to auto push and auto pull. It would set up clock dividers if we want to. And as we'll see in this particular example, the other thing that it's doing is associating a set of GPIO pins with certain instructions. So it'll associate pins with set commands or set instructions. It associates pins with out instructions. You can associate pins with the side set instructions. So let's take a look at this. The first thing that we do here is we create a PIO state machine config object called C, and we call a function that gives us all of the default configurations for this PIO program. We can go look at what those default configurations are. And then we go through and modify some of those default configurations. So in particular, we are specifying which pins are we going to be talking about when we call one of these out instructions, and we specify the destination for that out instruction to be the pins. Which pin or pins is that going to be? This is what configures that. So you can see that here, the first argument is a point, or the address of this state machine config object here. The second argument here is the GPIO pin number, which we're going to pass in. And then the third argument, if I recall, specifies how many pins to configure this way. So suppose, for instance, that we wanted to manipulate the values of 2 GPIO pins when we called an out command. So we called, out pins 2, so that we were shifting 2 bits out to the pins, shifting 2 bits out to 2 pins. The argument here would be 2, and the 2 pins that would get configured as the out pins would be GPIO number pin, right? The argument that we pass in here, maybe it's GPIO 25 if we're writing to the onboard LED, and the subsequent one if this argument is 2. So this would configure GPIOs 25 and 26 as the out pins. So there's a little bit of a constraint here where if you are manipulating multiple pins with a single instruction, say you're writing multiple pins with an out command, or you're writing multiple pins with a sidestep command, those multiple pins that you're writing with a single instruction must be sequential GPIO pins. We'll see this in the VGA driver with, for instance, the RG and B color pins. Those are all manipulated with, I can't remember which instruction. We'll take a look, but it's either I think it's an out instruction. So we specify the lowest GPIO number in this config set out pins instruction, and we put a 3 here because we're going to configure 3 color pins, RG and B. And then the GPIOs that get configured as being the ones that we're talking about when we say out pins 3 are GPIOs pin plus 1, and pin plus 2. In this case, we're only writing to 1 GPIO pin. So whenever we call out here, it's just going to be whatever pin that we've passed in as an argument to this function, which, as we just saw in the C code, is the Pico default LED pin, which, if we were to go look at this, is GPIO 25. So this is actually a 25. Okay, what else is happening in that initialization? We then call a PIO GPIO init on that pin number, which again, we could take a look at, but this is associating that particular GPIO pin with the PIO as being driven by the PIO coprocessor, in much the same way that we could associate a GPIO pin with, say, an SPI peripheral or with an I2C peripheral. In this case, we are associating that GPIO pin with the PIO. And then we are setting the directions of those pins. Remember that these PIO programs can read data in from the pins, and it can write data out to the pins. So in this case, we are configuring that particular pin such that it is an output. We're writing data out to it. And the arguments here are the PIO instance that we're manipulating, PIO 0. We pass it in as an argument, but it's going to be PIO 0. The state machine on that PIO instance that we're talking about, the pin that we're talking about, the number or the base pin that we're talking about, the number of pins up from that base pin that this instruction includes. So if we were writing GPIOs 25 and 26 as outputs, this would be a 2, and this argument would be 25. And then true is just to say that this is an output as opposed to an input. We then load so this init, this PIO state machine init, loads our program into the instruction memory and moves the program counter to the start of our program. And then this PIO state machine set enabled as an argument, it takes the PIO instance, the state machine that we're manipulating, and then true here means start the PIO program. If this was false or if this was commented out, then the PIO program wouldn't actually start. We can, if we want to, start the PIO program from our C program, which we might want to do if we're trying to do things like start 2 PIO programs on the same cycle instantaneously. There's a CSDK function called something like PIO state machine start enabled mask, which allows for you to start a series of PIO programs simultaneously. This too is used in the VGA driver to synchronize HSync and VSync. In this case, we're just starting this right away. Okay, so that's all the stuff that this initialization program does. So in the C code, when we call hello program init and we pass in the PIO instance, the state machine on that PIO, the offset as provided by this PIO add program SDK function call, and the GPIO pin that we're going to associate with that out instruction in our program. This does all the configurations and starts the PIO. So when that program starts, the first line of it is, sorry, I keep bouncing back and forth between these things, but let me just show you, let me just remind you of one more thing. The first line of this instruction is a pull. So as soon as we call this program that ultimately ends up starting the PIO, as soon as we call this function which ultimately ends up starting the PIO program, the first thing that happens is we hit this pull instruction, which will block until data appears in FIFO for it to move to the output shift register. So we start the program, it sits here and it waits for data to appear to in the TX FIFO. As soon as data appears in the TX FIFO, this instruction will execute, and when it executes, it moves that data into the output shift register. Then the next instruction will execute, and it moves the data, one bit of that data from the output shift register to the pins, the particular pin that we've configured, which is the LED. And then we jump back to the top and we execute another pull, or we sit and block here until data appears in the TX FIFO for us to move to the output shift register. And then in our C program, we are calling an SDK function, PIO state machine put blocking, that as an argument takes the PIO instance that we're talking about, the state machine on that PIO that we're talking about, and the data that we would like to write to that particular PIO's instances, that particular state machine on that particular PIO instance, TX FIFO. So this is a write to the TX FIFO of this particular state machine. So when we write a 1 here, that 1 appears in the TX FIFO. The PIO program sees the data appear in the TX FIFO. So the pull executes. This 1 gets moved to the output shift register. We then move to the next line of the PIO program, which is an out. We specify the destination to which we would like to shift data out of the output shift register to be the pins. So then a single bit moves from the output shift register out to our specified GPIO pin, which happens to be the one attached to the LED. It then goes back and waits for more data to appear in the TX FIFO. And it'll wait for a while because we write a 1. The ultimate consequence of this will be the LED turns on, right? Because the PIO program is sitting here waiting for data to appear. A 1 appears, that 1 gets moved to the OSR. That OSR gets moved out to the GPIO pin attached to the LED, so the LED turns on. Meanwhile, this goes back and waits for more data to appear. We then, in line 38, write a 0 to the TX FIFO. When that 0 appears, the 0 will be moved from the TX FIFO into the OSR. The out command will move the data from the OSR out to the GPIO pin attached to the LED, and the LED will blink off. So when you run this program, all that you will see is the LED going on, off, which is exactly the same output that we saw from the very, very first program that we looked at for the RP2040, the blinky example that just blinks an LED. But in this case, instead of manipulating that LED from the processor, it's instead the PIO program that's doing the GPIO manipulation, and our C program is communicating with that PIO program via these FIFOs, the TX FIFO. So this example, I hope that this is obvious, but this is not demonstrating the power of the PIO coprocessor. What this is demonstrating instead is how we get things to talk to each other. So this is one mechanism by which you can get your C code to talk to, that is to say, send data to a PIO program, right? And you could similarly, there's an SDK function that allows for you to read data from the RX FIFO that comes from a PIO program. And you could write programs that you could write programs in which your ARM processors and the PIOs interact in this way. As I've suggested a few times, and as we'll see, a really powerful mechanism for setting up the communication between the PIOs and the ARMs is via DMA channels, so that these writes to and reads from the FIFO occur with no CPU interaction. That allows for really, really high bandwidth communication back and forth between the processor and the PIOs. Okay. Let's look at one more example, and then I'll talk about the rest of them next time. So the next example that I want to look at is, let's see. Is also in this PIO directory. Let's take a look at, let's look at UART TX. Let's look at the PIO program. Okay, so there's a little bit more going on in this program, but not much. So let me just remind you first of all of the UART protocol. So I'm going to pull up. Let me just see here. I had some slides that we looked at a couple of lectures ago. I'll just pull them up to remind you. So the UART protocol is a really simple one. It looks like this. So the device that wants to send a UART transmission, the transmit line for that device, which is connected to the receive input of the device that's going to receive the transmission, is idle high, so it just sits high. And then when the device sending the UART transmission wants to indicate that it's about to send a transmission and that the receiver should get ready, it will do so by dropping that transmit line for 1 bit time. And it's up to you to specify how many clock pulses are associated with 1 bit time, but your bit time is your baud rate, right? How many bits per second are you sending? So the transmitter drops the transmit line, which is the signal to the receiving device to start its clock, so that the transmit clock and the receive clock are in phase, so that the device receiving data is checking the data on the data lines appropriately phased with the times at which the transmitting device is putting data on that data line, right? So the device that's doing the transmission drops the data line and then clocks out 8 bits and then raises the data line for 1 more bit time. This is the stop bit, and that's the full transaction, right? So it's a very, very old, very, very simple communication protocol. So let's look at how this is implemented in a PIO program. So similar to before, you can see that we have dot program and then the name of the program that we're writing. In this case, it's UART transmit. And then here we are specifying that we are going to have 1 side set pin. Remember, I mentioned that this side set is allowing for us to manipulate the value of up to 5 GPIO pins simultaneously with executing an instruction. So we can change the value of these side set pins on the same cycle that we are executing the associated instruction. And we can do that with up to 5 GPIOs. In this case, we're only doing it with 1 GPIO. And that side set pin is going to be, well, we'll see how it's used. So in any case, we're going to implement an 8N1 UART transmit. That is to say, each bit will be 8. What am I trying to say? Each bit will take 8 instruction times. So each bit, if the bit is high, then the transmit line will be high for 8 cycles. If the bit is low, the transmit line will be low for 8 cycles. So we start with a pull, Note here that this is, again, there's no block here. There's no other option. So this is a blocking pull. So this pull, when data appears in the TX FIFO, it will move that data from the TX FIFO into the output shift register. And when we get to this, while it's waiting, when we first get to this pull instruction, the other thing that it does is set the side set GPIO pin high. So we'll sit here and we'll block for as long as we're going to block. We just sit and wait for data to appear in the TX FIFO, sitting with the TX line high, which is what we want, because when we're not transmitting any data, we want for that line to be high, right? It's idle high. So we're just sitting with that data high. The data appears, and then the data gets moved from the TX FIFO into the output shift register. We delay for 7 cycles. The next thing that we then do is set the value of the X scratch register to 7. Remember that we're limited with this set command to values that are less than 2 to the 5th minus 1, so 31 or less. We can set values up to 31. 7 is less than 31. So we can use a set command to set the value of the X scratch register to 7. And meanwhile, we're using a side set command to put the side set GPIO pin to low. And then we're delaying for 7 additional cycles. So it takes 1 cycle to execute this instruction, and then we're delaying for 7 additional cycles, so that this whole thing takes 8 total cycles. This, incidentally, this going low is this transition here. So those 8 cycles are our start bit. We then get to this set of instructions labeled bit loop. And what we do is we execute an out instruction. Remember that out moves data from the output shift register to a specified destination. It moves a specified number of bits from the output shift register to a specified destination. In this case, what we're saying is move 1 bit from the output shift register to the pins, where, as we've just talked about down here in this initialization function, we specify the pins that we're talking about, the pin that we're talking about in this case. We move 1 bit out. We then get to line 17, where we say, jump back to bit loop in the event that the value of the X scratch register is greater than 0. So first, check if X is greater than 0. If so, move back to the start of bit loop and decrement X after having checked, which means that we'll loop here 8 times. Oh, and by the way, execute this instruction, but before you go back up here, delay for 6 cycles. Why 6 cycles? Well, it's in here that we are putting the data onto the data. We're putting the data onto the transmit line, and we want for each bit to be on the transmit line for 8 PIO cycles. So in order to enforce that, well, it's this instruction here that is causing perhaps some sort of a transition. Maybe the first bit that we're putting out is a 1. So that out instruction is going to set the associated GPIO pin high. So here's our transition. So that's 1. This evaluation here takes another cycle. We aren't modifying any values of the GPIOs here, so they are retaining whatever value they obtained up here in line 16. So we modify the data line here in line 16. In line 17, we're evaluating the condition, and meanwhile, the value of the GPIO is remaining the same. So after having evaluated this condition in this instruction, we will have been, the data line will have been at its present value for 2 cycles. And then because we want for each bit to be on the data line for 8 cycles, we delay for an additional 6. At which point we jump back up to bit loop. We shift out the next bit contained in the output shift register onto the pins and evaluate this condition, decrementing X. So first time through, X is 7, gets decremented to 6, 5, 4, 3, 2, 1. When X becomes 0, when it gets decremented to 0, we'll get to this jump condition. This condition will not be met. Meanwhile, we will have clocked out all 8 bits, right? So the next thing that happens after we clock out all 8 of our bits is we want our stop bit, which is the transmit line going high again. When this condition is no longer satisfied, which is to say X has achieved a value of 0, we no longer execute this jump. So instead of jumping back to bit loop, we jump instead back to the first instruction of our program, which is a pull. And meanwhile, when we get to this pull, we use a side set to simultaneously set the value on the transmit line high. That is this transition here. It's the stop bit. And then we sit here in this stop bit for at least 7 more cycles so that we have a full bit time of stop bit here. And then if there is another bit in the TX FIFO for us to transmit out through the UART channel, this pull moves that bit from the OSR, or I'm sorry, from the TX FIFO to the OSR, and then we go through this whole sequence again. Otherwise, if the user hasn't specified another bit to send out through this UART channel that we're implementing, it just sits here and blocks and waits for another character to appear in the TX FIFO. So the assumptions here are the user is putting characters, that is to say 8-bit words, into the TX FIFO for transmission out through this channel. And then the other interesting thing that's happening here that you may or may not have noticed is we are assuming that these side set manipulations, which are manipulating the values of some set of GPIO pins, we're assuming that this is manipulating the same GPIO pin as this out command. And in fact, it is. If we look down here at the UART transmit program init function, we can see that as an argument, this takes a series of arguments, some of which look familiar based on the program that we just looked at. So it's the PIO instance that we're working on, the state machine on that PIO that we're talking about, the offset, the TX pin, which GPIO pin are we using as the TX line, and the baud rate. And you can see here that these 2 lines of code associate particular GPIO pins with the side set instruction and with the out instruction. And what you can see is that we have configured the out instruction to manipulate pin TX, the particular GPIO pin that we pass into this function, as the one that we want for out to be manipulating. And also, we've configured it such that the side configurations, or I'm sorry, the side set instructions are also manipulating the same GPIO pin. So these two instructions, side set and out, are both manipulating the same GPIO. Now you can see there's no contention here because we are never doing an out and a side at the same time. In the event that we were, there is an order of priority here. One of them wins, right? But this is allowing for us to the side set is convenient because it allows for us to manipulate the transmit line simultaneously while we are simultaneously implementing some logic associated with the protocol. And then the out command is nice because it allows for us to shift data straight from the output shift register right out to the pins. And let's just briefly look at the C program. So what you can see here is we are specifying that the GPIO pin that we are going to use as the TX pin is going to be GPIO 0. We're specifying the baud rate here. We're going to use PIO 0. We're going to use state machine 0. This is a little bit different than the other example in that we aren't calling that SDK function that just says, hand me a free state machine. We're instead saying, no, I would like to use state machine 0 in particular. We are calling this PIO add program in order to get the offset in instruction memory where this program will live. And then we're calling that UART TX program init function that we put together in the .pio file. It's the function that we were just looking at where we were doing the GPIO configurations. And then what we do is we call a UART TX program put S. We specify the PIO we're talking about, the state machine we're talking about, and then a character string. And this function here is implemented in, I believe, yeah, it's implemented here within the PIO program as well, where you can see it's taking as an argument the PIO instance, the state machine on that PIO instance, character string, and then it is for each character in that string calling a put character, a UART TX program put character, which is itself implemented here. You can see that all this is doing under the hood is calling a more low-level C SDK function, PIO state machine put blocking. We're specifying the PIO instance we're talking about, the state machine on that PIO instance, and we are passing in the data that we want to write to the TX FIFO. And in this case, the data that we're writing to the TX FIFO is a particular character here, an 8-bit character. And I think this is likely obvious, but what's going on here is we're passing in a character string, a sequence of characters, and then one by one, we're writing each of those 8-bit characters to the TX FIFO of this particular PIO program. Those characters are getting pulled one by one via this pull command from the TX FIFO into the output shift register. And then each of those 8-bit characters is being put out bit by bit onto the TX line, with some logic in here to enforce that there are 8 PIO cycles per bit. And incidentally, where is the baud rate being enforced? Well, it's here, where you can see that in this particular program, we are implementing that clock divider that I talked about earlier, this feature that allows for you to slow down a state machine relative to the system clock. In this case, what we're doing is slowing down the state machine such that the data that appears on the transmit line appears at the specified baud rate. Okay, so what I want to talk about next time is I want to take a look at the UART receive example. I want to take a look at the SPI example. Why? Because you're familiar with the SPI protocol. So I think it's nice to look at PIO examples for familiar protocols. And then after having done that, I want to talk about how the VGA standard works. And then we'll look at a PIO implementation of that standard. So that's the plan for the next, probably 2 lectures, lecture and a half or so. Okay, sounds good. I will see you all very soon.